this is the second question of the final of Physics 101 in spring 2018. You're asked to consider a system made up of two masses M1 and M2, and initially there's a spring which is stretched by an amount delta between them. And then we basically let the system go. So first part asks us to find the accelerations of the masses at the moment the string is cut, at the moment the system is actually left free. What would be the force on the spring? Well, it will be just k times delta, right? The amount of compression, that's the magnitude of the force. But how does this act on my masses M1 and M2? It actually acts on both, right? This is going to be the force in different directions. That's the initial situation. So what will be the acceleration of the first mass? It will be just basically F over M1, which is going to be K over M1 times delta. And A2 is F over 2. It's going to be K times delta divided by M2. So it's the first part. What are the final velocities of the masses? Now, during all this process, momentum is conserved, right? What does that mean? After these objects basically leave the spring behind, if their velocities are v1 and v2 in opposite directions, I know the following: m1 v1 must equal m2 v2. But also during this process there is no dissipation, there is no force which is not conservative. So energy must be conserved. Which means my initial energy, there is no kinetic energy initially, all my energy is stored in the spring. That must equal the final energy, which is going to be 1/2 m1 v1 square plus 1/2 m2 v2 square. So let's cancel all these 1/2s. I have k delta square is m1 v1 square plus m2. Instead of v2, from the first equation I'll write v2 is essentially m1 divided by m2 times v1. m1 divided by m2 square v1 square. So on the right hand side, what do I have? I have m1 plus m1 square divided by m2 times v1 square. So from here, v1 I will actually find as k delta square divided by m1, 1 plus m1 over m2 square root. Or I can basically write this as k m1, 1 plus m1 over m2 times delta. K over m has units of 1 over second, so delta has units of length. That is length divided by time, meters per second, so unit-wise it's okay. Now I can just multiply this by m1 over m2, which will give me k divided by m2, 1 plus m2 over m1 times delta. I did not actually do the multiplication. I just changed all the indices to index 1 because the problem essentially doesn't know what we call them 1 and what we call them 2. So by just changing the indices, I will get the correct result. Now part C is the more interesting part. If m1 is equal to m2, how long does it take for the spring to reach its relaxed length? So you're asked to consider the following situation. Initially, I have m and m. Then at some point here, the velocities are 0. Then I reach a point where essentially the spring loses contact with both masses. And the problem is, how long does it take for this process? Now, energy conservation would not help us. Whenever we have to find something which depends on time, energy conservation does not tell us that time. It's not possible to. We have invented energy conservation just to get rid of time dependence. So what should we do here? Maybe we should actually think about, maybe we should be imaginative here. What would happen if the spring was actually tied to the masses? So instead of losing contact, this process kept on going. Well, if the spring was tied to the masses, the system will clearly oscillate, right? The masses will actually stretch a little further, stop, come back, and do all this process again. So the time it takes to go from here to the maximum velocity point is actually 1/4 of the period of harmonic oscillations, right? If I waited 4 times this process, and if the spring was tied to the masses, then I would see a full period of the oscillations. So what is the period of oscillation of the system of two masses tied by a spring K? Well, clearly the system will oscillate around the center of mass. So the center of mass point will be immobile. Maybe I should think of this as a mass m tied to a spring, which is half the length. Now what does that mean? If I stretch this by x, the full spring will stretch by 2x. So this is essentially equivalent to thinking of a single spring with spring constant 2k. So what would be the frequency here? 2k over m, right? So what would be the period of the motion, which would be 2 pi over omega, right? 2 pi divided by square root of 2k over m, 2 pi square root of k, and the time it takes will be just the period divided by 4, so it's going to be pi over 2 square root of m over 2k. This part actually did not require much calculation, but it required a lot of imagination, so this was actually a hard problem to solve.